All right, so we're starting section 2 today, which is using Newton's laws. Okay. And the first thing that we're actually going to talk about is that weight force. Okay, we're going to kind of see how does Newton's law, mainly his second law. So Newton's second law, the net force acting on an object is equal to its mass times its acceleration. We're going to see kind of how that applies in different contexts. Okay, so first we're going to actually look at the weight force acting on an object. Okay, the weight force. So if I have an object in a free fall, so imagine some type of ball falling. Okay. If it's in free fall, we're going to say the only force acting on it is F sub g, right? It's the force due to gravity. Okay. So in that context, the net force is going to be F sub g if it's in free fall. So we're ignoring air resistance. Okay. Then that is going to be equal to its mass times its acceleration.
Which is 9 point.
Right. For objects near the surface of Earth, if we ignore air resistance, they're all going to have uniform acceleration, and that is just that lowercase g. Okay, and again, that g near the surface of Earth is going to be
9.80.
right. So all objects are going to experience, all objects in free fall are going to experience that acceleration. If they have a greater mass, there's going to be a greater force, but they also have more inertia, so the acceleration ends up being the same. Okay. All right. So that means, and again, if we think about this, it gives us a way to calculate an object's weight. Okay. It is the product of its mass times the acceleration due to gravity. Okay, so that's actually how we calculate the weight of an object. Again, weight changes if we go to a different environment like the moon or Mars. The mass would stay constant. So for example, also I should clarify, because we're used to having a weight measured in pounds, for SI units, this is going to be 9.8 meters per second squared times the mass in kilograms, and the product of those two things in SI units is always going to be this force in newtons. So just kind of maybe think about weight differently. Weight is actually a force. Okay, and it's going to be measured in newtons. We're not going to work in pounds mainly. You can convert, but the SI unit, if we're dealing with kilograms, meters per second, the weight is going to be measured in newtons. So for example, a 10 kilogram object near the surface of Earth with an acceleration of 9.8 meters per second squared, the weight would just be 10 times 9.8 would be 98 newtons. Okay, makes sense? All right. So then that changes a little bit, or I guess there's kind of some misconceptions. Well, what happens if you have a falling object and it becomes, as velocity increases, air resistance increases, and we get to a point where it's not really in free fall anymore, that acceleration changes, okay? The weight doesn't really change, okay? The reason is this acceleration due to gravity does not change, okay? The gravitational force exerted on it is still the same. Its free body diagram, instead of just being in free fall, would now maybe look like that, with a force due to friction acting on it. This, which is the weight force or force due to gravity, does not change, right? The net force changed. So the acceleration, basically then it would go to this type of problem. Okay. but we can still use that to calculate an object's weight. We'll do some examples here in a second. So just kind of to maybe kind of wrap some of that up before we move on. A 10 kilogram object, if I take it to the moon,
Yeah.
what changes and what stays the same?
The mass stays the same.
Mass is going to stay constant.
Force of gravity changes.
Yes, so its weight will change. Again, because the acceleration due to gravity is different in that place. The force due to gravity is different as well. Okay, so we'll do a couple quick examples here kind of using that. And again, we can use that acceleration due to gravity is 9.80 meters per second squared near the surface of Earth, and that is constant even if an object may not experience that acceleration. Okay, acceleration due to gravity is still that. So just be aware of that. Okay. So we're going to find what is the mass of an object that weighs 2,300 newtons. Okay. So how did we do that? First off, we need to understand this 2,300 newtons. That is F sub g, right? And then we're solving for the mass, and we know g is constant. Okay. Even if this object is sitting on the floor, not moving, we still use this g, that acceleration due to gravity. This is really, and it may seem kind of confusing, but this is really like an indicator of the strength of Earth's gravitational field. Okay, so even if an object isn't accelerating at that speed, it's still indicative of the force acting on it.
Yeah.
Okay, so we just plug that in. The weight is F sub g in newtons. And then we're just solving for the mass. So you would divide both sides by 9.8. And we said 235
Yeah.
kilograms. Okay, good. So now we're going to talk a little bit about pounds. If I want to know the weight, so what is the weight that doesn't seem right. No, it's not 25. It's supposed to be 75. I was going to say that doesn't sound reasonable. So we're going to find the weight of a 75 kilogram man in both newtons and in pounds.
It's 735.
So anyway, this is how we're going to use weight 99% of the time in physics, because again, this is the SI unit that works with kilograms, meters per second squared, all of our default units. But if you want to go from this to pounds, 1 Newton, and you might want to write this down, equals about, I guess I should use, it's about 0.22 pounds. Okay. So this would be, if you multiply it by 0.22, we get, what'd you say, 165?
Yeah. No, 162.
162. Okay. Again, that seems reasonable. We're talking about the weight of a man, about 162 pounds. So, to reverse that process, how would I go from a weight in pounds to a weight force in newtons?
Just divide it by 0.22.
Yeah, you could just take this divided by 0.22. Newtons are always going to be, you're always going to have more newtons than pounds.
Yeah.
Okay. So just keep that in mind. All right. So one thing I want to talk about, just to address a misconception, we're not going to go into a lot of detail here, but we're going to talk about moving objects. Okay. And a lot of times, it seems kind of deceiving. If I want to push an object sideways, if I exert a constant force on it, a lot of times we think, okay, it moves at a constant speed, and that can be kind of deceptive. It actually can end up happening, but that's because friction changes and stuff. But I want to kind of think about, if I put a net force on this object, so there's friction, I overcome that friction with a greater force. So here's like the force of me pushing on it, and there's a smaller force of friction. I cause an acceleration, right? That object begins accelerating. And if nothing changed, so you have an acceleration of something. If those factors don't change, that object would continue to accelerate, right? Not move at a constant speed.
Yeah.
The reason that it ends up moving at a constant speed a lot of times in reality is because this force of friction, things change, or a lot of times we actually change the force that we're pushing on it. You give it a bigger push to get it moving, and then you actually change the amount. We're used to actually moving things at a constant velocity, not maintaining a constant force on it.
Yeah.
Okay, so just understand there is sometimes a difference between the way things appeared to work and the way that they actually work kind of under the surface. Okay, and again, that's why a lot of times it's helpful, I think, to think about like outer space or a frictionless environment.
Because if you kept putting force into it, it'd get faster.
All right, think about a rocket. If it's emitting even a very, very low force of thrust, that may have a low acceleration, but it can continue to accelerate and accelerate and accelerate because there's negligible amounts of friction on it. So anyway, just wanted to clarify that before we jump into this problem, because there are some things that if we're thinking about the way things tend to work and we don't account for some of that stuff, it can lead to some problems. So say we want to lift a 35 kilogram rock. So we have a 35 kilogram rock. And we want to lift it, and so we exert a upward force of 502 newtons. It's 502 newtons upwards. Okay, and we want to find what is its acceleration. Okay, because again, if we're lifting it, if we cause that net force that causes an acceleration, it's going to accelerate, not move at a constant velocity if those conditions remained constant. So this, we're going to go back to the net force. Now, what was your initial reaction to do there?
Divide the force by the mass.
Okay, and that would seems like a completely logical thing to do,
It's not.
but it's not,
Why?
because of Newton's second law. It is the net force that affects the acceleration due to an object, and this is the easiest mistake to do. The force that we're putting on it there is not the only force on the rock. So this is actually going to be really, really important to draw free body diagrams. Okay, make sure you include all the forces. Because if we've got let's pretend that's the ground. If I've got this big old rock here that's 35 kilograms and we're trying to lift it, it's not an environment like outer space where it's just a completely weightless rock and the only hindrance to us accelerating it is its mass. If we draw a free body diagram, we have the force that we're putting upwards on it of 502 newtons. What other force is there?
Gravity.
Yes. So you always have to take that into consideration. Now, if we're assuming that we're going to lift it, gravity has to be less, right?
Yeah.
So I have to actually calculate F sub g. How do I do that?
Multiply the mass by the force of gravity, which gets
By the accelerate, that
Yeah.
9.80 meters per second.
get like 343.
Okay. So F sub g is 343 newtons. Okay, that's acting downward. So yes, there is a counteractive force acting on this rock. So if we want to begin accelerating it, we have to exert at least 343 newtons, right? Okay, so what we need to do is actually find the net force acting on the rock.
So subtract 343 from 5.
Yep. Which would be
159.
159 newtons upward. Correct?
Yep.
Okay. So that is the net force that we're going to use here, not just the force that gives you. Okay. Be careful. That's a really easy mistake to make that a lot of people make. That's why I really, really recommend free body diagrams. I would like to see this on almost every single problem. It's pretty quick and simple to do. It just helps you make sure you account for everything before you start plugging in and calculating. Because it is really nice to say, well, hey, we've got a mass, we've got a force. All I need is acceleration, right? But you need the net force, okay? So always find the net force before finding acceleration. Now that I've got that 159 newtons, now what do I do?
Now you can divide it by the.
Right, I'd plug it in here. That is the net force. And we know it's mass. 4.5 what?
Meters per second squared.
Yep, very good. And there we go. So yeah, pretty easy. You're just using Newton's second law. Just be careful to find the net force. We'll go ahead and take, I'm gonna maybe take out a lot of the detail because again, some stuff there makes it not quite as accurate as I would like. So basically we have two people pulling on this doll in opposite directions, and the doll has a mass of 0.3 kilograms.
Yep.
Actually, I think there was an extra zero at the end there for sig figs. So I'm gonna say Anne is on the left and Sarah is on the right. You don't have to set, again, this kind of comes into your choices in coordinate systems. That's just how I chose to set it up. And it says that Sarah pulls with a force of 10 newtons. Okay, so this is the force from Sarah equals 10 newtons. Okay. And then it says the doll begins accelerating away from her, and I read this as away from Sarah at an acceleration of 3.3 meters per second. So the acceleration is 3.3 meters per second squared in Anne's direction.
Yeah.
Okay. So we could decide that that's an, how do you want to set this coordinate system up? We could decide that that's negative, this is positive.
Yeah.
It doesn't really matter to me. I'm going to go ahead and adjust my free body diagram because I know that Anne's force has to be greater. Okay. And again, for this problem, I'm going to ignore the mass of both people. Okay. It only gives us the mass of the doll. In real life, the mass of each person would probably come into play. We're going to overly simplify it here. Okay. So, since Anne, her force is greater, the acceleration is in that direction, I need to decide on a coordinate system. I'm going to decide that that direction is positive, that direction is negative. So that means this acceleration has to be negative. Okay. It wants to know what is the force that Anne pulls with. That's what we're trying to find. Okay? So we've got the acceleration, we've got one force, but not the other. What do we need to do?
Couldn't you divide the force of Sarah by the mass and get her acceleration?
The acceleration of the doll is going to be the same.
Yeah.
Again, I'm going to go back. Here's Newton's second law. We have the acceleration. We have the mass.
Wait, yeah, just multiply those and then you get your net force.
Okay, we can find the net force. Okay, so if I multiply mass times acceleration, it should be like negative 0.99.
Yeah.
Okay. So, and again, that force, that net force is negative. That makes sense if we look at our free body diagram and the acceleration. If I know the net force, can I use that to solve for Anne's force?
Yep.
Okay. Basically, how I would break this down is the net force is going to equal the sum of those two. Okay. It's going to end up negative because this the force due to Anne is going to be a greater negative value. So we know this. So I'm just going to substitute stuff in here. Negative 0.99 is our net force. We don't know Anne's, and Sarah's is 10 newtons. So then we just solve. And it would be that. And again, you should be able to kind of double check this, make sure it makes sense. If this is Anne's force and this is Sarah's force, that would make sense to get a net force of negative 0.99. And then if I double check, just using Newton's second law, is the mass times the acceleration. Yeah, you can kind of go through and verify everything after you've solved. Cool?